I hope everyone can hear me. I'm speaking as loud as I can, but I'm going to introduce two speakers who I think are going to provide a really insightful presentation on some of the things that are happening with the AFX laser up in Hamburg, Germany. And so first up is going to be Philipp Kohlwes, and following that is part of the same talk, Frederik Bruel will be speaking as well. And first, Philipp is a team leader at the Fraunhofer IAPT. He's responsible for powder bed material processes, where he conducts research on productivity enhancement, cost reduction, and system component development. Frederik is an application engineer for Materialise's data preparation software. He assists research partners and machine OEMs with integrating the Materialise Control Platform solution into laser-based AM machines. So with that, I want to give it to Philipp, please.
Thanks, Rob. So, good morning also from my side. As Rob kindly introduced myself, I'm Philipp Kohlwes, working at the Fraunhofer IAPT as the head of the powder bed metal group. And I shortly want to introduce you this topic about the higher productivity using beam-shaped laser in combination with Materialise MCP in our facility where we did some research on it. Quite nice to see that it arises so much interest. Nice to see you all, and if you have any questions at the end, please contact us. I will highlight only some nice few slides to show you the potential, because it's an ongoing project and therefore I can of course not share any details in the depth. But there will be some further project, and the idea is of this talk that you can be a partner in our consortium together with Optoprim, nLIGHT, Materialise and us together, and therefore if anything is interesting for you and your facility, please get in contact with us. So the whole talk is divided into separate topics. Short motivation, only one slide, where I show you that the potential or the idea is why we want to use ring mode lasers. Some preliminary works in our facility from several years, because we're dealing with beam-shaped technology since, I don't know, several hundreds of years, more or less, but then using more or less optics, which we include into the optical bench. I share you some topics about the machine setup, show you some first single track results, 2D experiments, some density cubes and some conclusions which we found out. So the general idea of getting to further productivity. So with regard to the motivation, I think you all know that we have that the process or the productivity of the process in general is limited up to the beam profile or the maximum energy input that you can put into the material, and therefore if you use other beam shapes, we have made some simulations and so on, then you can put more and more energy into the whole powder, into the melt part, and therefore you can reach higher build-up rates. And the typical used Gaussian beam profile, which is shown here, leads to an imbalanced temperature profile into the whole system, because you have way too high energy here, which can lead to vaporization and some, let's call it, loss of energy here on the boundaries, where you have simply not enough energy to melt something or have a homogeneous melt track at the end. And these findings, or the motivation of these findings, is that we have used one single laser source, and that you can transfer it to multi-laser sources where you can benefit from all these achievements here. So these are some preliminary works, done with beam or with ring mode lasers, so with some optical things. For several years we made some research on it, and we found out that we have, for example, no balling and protrusion, no keyhole welding, more stable depths of the melt pools and wider melt pools, and these things are added up with more stable processes and additionally higher build-up rates. And this is the motivation of using these type of technology, and we have also done some preliminary works where we tested, for example, the mechanical properties. You can see here directly on the blue y-axis the ultimate tensile strength, and on the right the red one, the elongation at break. And on the bottom you see on the x-axis the theoretical build-up rate. We have made some tests, so the state of the art is having a build-up rate of approximately 37.5 cubic centimeters per hour for aluminium silicium 10 mg, with an ultimate tensile strength of 450 and, for example, elongation at break of 4%. And with using beam shaping, we have achieved the same or even higher values. In this case, a little bit higher, but we have made it for different alloys like aluminium, steel, and so on. So different research investigations state that you do not lose any mechanical properties while keeping the theoretical build-up rate very high. And from these preliminary works, the thing was that the scalability for serial production was not guaranteed. And the idea was, then I get in contact with Christian from Optoprim and with Frederik from Materialise, and we had the idea of putting it in a more stable system, and therefore we implemented such a ring mode laser system into a conventional and widespread AM system on the market. So not using research machines, so putting it directly into a widely spreaded machine. And therefore we come together and made this kind of project here. I will skip this, so I will not talk in detail about every detail on the slides. So here the machine setup, you see the different indexes and the different shapes, and we're focusing on having index 0, index 4 and index 6 in our investigation as preliminary results, and therefore we made these investigations, so the donut shape, the Gaussian profile, and a mixture of both with a little bit higher Gaussian profile in the middle still. So the single track results you see here directly, I put on the x-axis the laser power in watts and the single track width in micrometer on the y-axis. Have two different setups while increasing the laser power and while keeping the laser power the same level. And what you see directly here with an increasing laser index, of course, the whole thing is widened, the melt path which is existing then, and the hedge distance can be increased. And I compared index 6 to the Gaussian profile, which was approximately 220% wider, and therefore you can increase the hedge distance on a way higher level there. And the thing is, you not only can put more energy into the melt pool, but you are forced to put more energy, which is nice for productivity purposes. And therefore we go on with these values from the single track results and go further on the 2D experiments. Here you see some tables or graphics where I compared the hedge distance over the scan speed. So scan speed increasing to the right, hedge distance from the specific values of each index increasing to the bottom, and you see here that you have some good, average and bad. So I made it more professional on the real things with investigations, but you see you have much wider values here, or much areas, which also indicates that you have that is not so problematic to run out of these boundaries here if you keep, for example, in the middle. And from these research results I went over and plotted it again, hedge distance over scan speed, and indicate only the good ones. So the surfaces which had a good quality showing up, which leads to possibly a good density here. And the index 0 showed only two values where the good results are achieving here. And then, for example, index 4 shows much wider and higher productivity. And the index 6 also going up here, so bigger hedge distance, increasing the scan speed. So your aim is to go here to have a high productivity, and therefore you see, okay, index 6 has a way higher productivity increasement achieved. With these results, I went over to the 3D experiments then, where we made some tests with laser index 0, 4 and 6. And here are some exemplary results. So not choosing the best or worst one of each, so exemplary for the whole build setup, which started with the single track results. So with index 0 you see mainly porous more or less, and you see directly in index 4 and index 6 leads to values up to 99.99%, so nearly no porosity was detected, but this were really impressive for us too, to see these direct changes here. Then I also plotted in with regard to the density, so the scale is lower than 99.6% density, 6 to 8, 8 to 100%, and you see the same thing here that you have, for example, in laser index 6 and for a very wide band. And what is very interesting is that you do not have any boundaries here. So therefore I concluded that you have way higher further potential to increase the build-up rate, way higher than we did it here. So the further potential is quite nice to know. I will come back to this at the end again. And I plotted again hedge distance over scan speed, only the values of having bigger densities of 99.9%. And you see here index 4, again, high accumulations in this bottom area here, and index 6 way higher, so best results achieved here on this level. And the nice thing is that you have increased your productivity while keeping the density at a high level here. I also made some high-speed videos. This is only with 3000 FPS, which looks quite nice because you see in normal colors something. This is index 0, which is scanning here, and afterwards index 4 and 6 is appearing, and you see in this case, which was also quite interesting for us, because in preliminary works we found out that beam shaping leads to less spatter and smoke and so on. In this case we don't know yet, but it leads to more spatter and more smoke. But this is definitely not a big problem because we built big samples and the quality was very good. So this is definitely a point we will further investigate, but just to let you know here. Then the conclusion is we compare it to the state of the art. So from typical machine suppliers where they put the data online. So machine supplier 1, machine supplier 2, and these are the values of the official data sheets, and we compared the same layer thickness for all 3 suppliers. So right y-axis is the density. In green on the left y-axis you see the theoretical build-up rate, and we compared these values here, and it doesn't work. No. The typical values for machine supplier 1 was approximately 37.5, the same for machine supplier 2, and the density which were given in the datasheet were 99% and 99.8%, and while using beam shaping technology in combination with the MCP from Materialise, we were able to go further. So the new process we found out there is approximately 3 times faster. So using a single laser source with a ring mode laser, for example, leads to a build-up rate of 103 cubic centimeters per hour, while keeping the density of nearly 100%, so 99.98% I think it was. And therefore, again, we see some further potential coming up here, because we definitely can decrease the density, because no one needs a density of 99.98%, and we can further increase layer thickness and using even wider shapes and so on, and therefore there's a high potential of increasing build-up rates. To conclude shortly, we have achieved these values here, okay, 99.97%, and we showed the further potential. What will be investigated from our side more is the smoke and spatter thing, because it's quite interesting. We had a lot of experience in beam shaping, and this was the first time that we saw the opposite behavior here. But we are very, very sure, even out of simulations and so on, that a different small change will lead to the same thing, that we have less spatter and less smoke appearing here. And the results of the mechanical properties will come in the next days. But the thing is, we saw in our preliminary results also, which I showed you in the beginning, that we have, for example, the same or even better mechanical results here, and therefore we are quite confident to reach it also. We have achieved, of course, a little bit higher surface roughness here, because you have a wider beam, wider hedge, and therefore you have to use contours, which is definitely no problem, and some edge porosity. But we are already done with the use of the MCP, the innovative control algorithms, where we can program individually what we want to achieve, and therefore we already reduce the surface roughness to a normal level, even sometimes better. And this will be the part of Frederik to show you what is the MCP in general capable about. And again, we are looking always for partners in our consortium, so if you are interested in, talk to me later, talk to Frederik, talk to Christian or Rob, and we will come together. I will hand over to Frederik now, and he will tell you something about the part of the Materialise. Thanks.
Thanks, Philip. I'm Frederik, did the software on the machine at Fraunhofer IAPT to realize this nice groundbreaking experiments that Philip has conducted. We as Materialise software really see that the additive manufacturing landscape is changing rapidly, more from like prototyping towards real serial manufacturing. And in serial manufacturing, reliability and also the productivity that this new technology offers is critical. And that, of course, we want to embrace with our Materialise software technologies.
There it goes. Yeah.
Just
The bottom down.
Okay, so as Materialise software, we see basically two challenges for our partners, machine vendors or research institutes. One challenge is that the technology is improving fast. We see like multiple lasers on a scan field, multiple scan fields next to each other, lasers working together in machines with different beam diameters, but now also these nice indexes that can change the shape of your beam to increase the productivity. Of course, our software needs to follow. And that's what we're doing on a day-to-day basis. But we also see a next challenge. All these machine vendors, they want to differentiate on the hardware level, but also on the software level, tailing more towards automotive, dental industry, more towards productivity or quality. And yeah, we are presenting you these tools that should allow the machine vendors to actually achieve this. One of these is the build processor SDK and our Materialise Control Platform, the controller inside the machine that enables the research that we have done. First of all, I will need to explain what the build processor actually is. The build processor is a bit the translation layer, like in a 2D printing landscape. A driver is in an operating system. You have drivers for HP, Canon printers, for laser inkjet technologies, and this will translate the information in a Word document to something that the 3D printer is able to execute. In 3D printing, we have a similar story. We in this use the toolpath generation software that translates the mesh as an input coming from Materialise Magic software, but also CAD packages like Siemens NX or PTC Creo, and translating that into something that the machine is able to read. That's what we call our Materialise job file. That job file is a standardized file that contains all of the material-specific parameter sets to allow the good execution of the part being printed. And we can announce already that we will also incorporate that new beam index, allowing you to shape the beam for different sections of your parts or geometry. If you have this job file that has all of the material-specific parameters controlled by a parameter set managed in our build processor, it should go towards the machine. And on the machine, we also have a powerful controller that's equipped with our software that allows to translate these instructions to easy commands, like load the job, and then load the layer, and then scan the layer. Scanning the layer will just translate these inputs in the job file towards commands, towards the mirrors that move the lasers on the platform, and also to communicate, for example, the beam index and the power that the laser needs to produce to get the right quality at the end. These partners, machine vendors, research institutes can integrate in their machines to very easily create a state-of-the-art machine with the latest technology in them. We also see a next challenge, as we already mentioned. All of these machine vendors want to differentiate based on their own IP. They are using beam indexes, multiple beam diameters, more lasers. But they also want to differentiate it for different niche markets. So general purpose product is not always a good thing. For this reason, we are also announcing here that we are releasing a software development kit in Python that will allow you to access the building blocks of our Materialise 30 years experience in creating software for AM machines. And allowing you to use it from a Python environment to really tailor the toolpaths for the new technologies that will come in the future and embracing the hardware that nLIGHT is offering to achieve like newer and better prints with higher quality and even more reliability. If you want to start using it, we are at the moment releasing it. Our APIs towards our Magix application and the graphical user interface to create parameter sets and so on is already available as of today. Then from January onwards, machine vendors or research institutes can jump on the train and start using that SDK to produce the toolpaths that will drive the next generation machines together with these nLIGHT new beam shapes that are announced over here. And benefiting from the results that Philipp has shown in his research. If you have more questions or looking to doing such a project together with Materialise, you can come and visit us at the booth upstairs at the entrance. And thanks a lot for all of your attention, and hopefully you have enjoyed the show.